So last time we are trying to study Berlekamp algorithm as a reduction strategy, and so first thing that we did is to define resultant for two polynomials. What is this invariant polynomial called resultant? And we showed that we showed this lemma that if GCD, if A and B are co-prime over the function field x1, so we are thinking of AB as a univariate in x2 over fx1. If they are co-prime, then this Bezout identity UA plus VB will give you resultant. Okay, in other words, resultant is in the ideal of A comma B, and remember that resultant is a univariate in x1. Okay, it eliminates x2. So we showed that. Any questions about this? So this is what we have done. So we have shown that resultant is in the ideal of AB, and we also are degree limited as in the Euclid algorithm case. So let's write it down in terms of the ideal. So resultant is in the ideal A comma B over bivariate polynomial ring, and it is also univariate. Okay, so resultant is a univariate in x1 and it is in the ideal. That's the property. So when A and B are co-prime over the function field, then resultant is in the ideal, we have seen. And what happens if A and B share a factor? They are not co-prime. Why is the resultant then in this? Yeah, so in that case resultant is 0, right? So in both the cases it is in the ideal. This is without any assumption. And the earlier statement was for univariates. So for univariates, resultant is in the ideal, is also in the ideal A comma B intersection F. Okay, because for univariates, if the univariates are co-prime, then the resultant is non-zero. It's actually 1. You can take it as 1. Why is 1 in the ideal A comma B? Well, because A comma B are co-prime, so actually A comma B will generate everything, right? So this is happening over Fx. So when A B co-prime, this is correct, and when A and B share a factor, then the resultant is 0, and 0 is in the ideal. Okay, so this is the green thing is for univariate, and the above fact is for bivariate. They look similar. Is that clear? So this is something to remember. And what is the degree of the resultant? So degree of the univariate resultant which is a univariate polynomial in x1, this is at most so remember that it was the matrix given by the linear system to find u and v in Euclid algorithm, right? So it is related to it's basically the matrix dimensions are sum of the degrees of u plus degree of v. but then that you will when you compute the determinant, you will have to take the product. So it's kind of quadratic. So it is degree of b with respect to x2 times degree of a with respect to x1 plus the symmetric thing. So we'll use the bound twice degree of a times degree of b. So if you exactly write down the matrix and check the determinant degree, you will get this bound. It's basically product of the degrees of AB, which is the total degree. So degree with respect to both x1 and x2, all variables. Product of that and this factor of 2. Okay. So resultant is we say that resultant is a low degree polynomial. It is univariate and it is contained in this bivariate ideal. Okay, so that finishes the discussion on resultant. Next thing we will do is the reduction of factorization. So say you have an algorithm that can factorize polynomials over prime fields, FP. Okay, how can you use this algorithm to factorize polynomials in the extension? Right, and this is non-trivial because polynomial which was irreducible in the prime field, when you go to an extension, it can easily reduce. Right, so in the prime field, you did not need to factor the polynomial, but in the extension, you will actually have to find roots. So it is highly non-trivial that these two things are actually related. On the other hand, if you can factorize over FQ, can you factorize over FP? Why is that?
You just have to multiply some factor.
Exactly. So FQ is a bigger field. So if you can find factorization over FQ, then to find factorization over FP, you just have to cluster the conjugate factors. Okay. So if you, for example, if you can factorize over complex, then you can factorize over reals, because the conjugate of square root of -1 is minus of square root of -1. So you just have to cluster the conjugates and multiply them, so you get a factor in the lower field. So FP to FQ is actually trivial, but FQ to FP is non-trivial, right? So the non-trivial thing we'll do, and then the two will become equivalent. Over the finite field FQ. So you are given a polynomial fx, and this factors into so recall all these results we had about factorization over FQ, right? So we can, by pre-processing steps, we can assume that fx factors as equidegree irreducibles. So it factors into k equidegree co-prime irreducibles. in FQX. Right. So, this is the setting we are in. So, now we want to find these equidegree factors, irreducible factors, given a subroutine to factor FP polynomials. Right. This is our goal. So, that is what now we will show. We will show that factoring over FQ reduces in deterministic polynomial time. This is not prime P, but polynomial time P, the complexity class. It reduces into factoring over FP. Okay, where Q is a power of P. Q is P square, P cube, so on. So, we will give a deterministic polynomial time reduction from this first problem to the second problem, thus making the two equivalent. So, further recall Berlekamp algorithm. Right. So, Berlekamp algorithm will give you a G such that, so degree of G is less than the degree of F, which we are calling D. So, G's degree is between 1 and D minus 1, and G raised to P is G mod F. Right. So, this we were able to find by linear system solving, a non-trivial G such that this happens. So, this was step 1 essentially of Berlekamp algorithm. Step 2 was that you will then take GCD of G minus alpha with F for all alpha constants, numbers 0 to P minus 1. Right. So, that was the part which was expensive if P is large. So, we will actually modify that. So, the second step, which was taking GCD of Fx with G of x minus y, right, varying y 0 to P minus 1. So, that we will now not do. Instead, we will actually say that, look at the resultant. And call this. So, think of GCD taking GCD of these two bivariates. Y, think of y as a formal variable. Okay, do not fix y to a number. And so, you are interested in GCD of these two things with respect to x. So, analogously you should take resultant of these two. When you take resultant, this becomes a univariate in y, right. So, let us call this hy. So, you compute this. So, whatever you have learnt about resultant, using that you can compute it in deterministic polynomial time, and now what is the connection of this with factors of f? What do you know? So, in the context of Berlekamp algorithm, you know that some number y would have worked and given a non-trivial GCD, right, which means that that number, let us say alpha, what can you say about H of alpha? Right, so all those good alphas are actually roots of H, and they are numbers, right? So here you can call the subroutine that factors over Fp. So if you have a subroutine, if you have an algorithm that factors over Fp, it will factor H and it will give you the alpha, and then you happily compute step 2 of Berlekamp. Right, that is the fast algorithm. So that basically is the proof. So by the properties of resultant, we know that an Fp root of H always satisfies this. And this Fp root I am calling alpha. And actually this is for any Fp root. Let me clear this. So any Fp root alpha of Hy will share a non-trivial GCD with F. G minus alpha will share a non-trivial GCD with F. And any alpha for which the GCD is non-trivial has to be a root of H. Right? It's if and only if. Nothing is lost in H. So we can make this in fact okay. So any questions about this? This is the main crux of the proof, right? That you observe GCD is non-one if and only if alpha is a root of the resultant. So you compute the resultant and factor it. This is the constructive proof. So instead of searching for alpha, simply factorize this polynomial. So you are only interested in the roots of H, right? Not quadratic factors or cubic factors, linear factors. So you can extract them by taking GCD with this, right? Y raised to p minus y contains all the roots, and it is also efficiently reducible mod H. So you first reduce it by repeated squaring mod H, then take the GCD. Call this H1. So now H1 only has roots. Okay, it doesn't have any other irreducible factor. So on this H1 you apply your subroutine. H1 completely splits. And has good alpha as roots. Okay. So one thing here is, what can you say about the degree of H and H1?
Degree of H1 is
So first, what is the degree of H? So degree of H is not, it is not more than 2D square. In fact, it is not more than yeah, not D square. I mean, we had some factor of 2, so it's something like 2D times D minus 1. But you should also note that this situation is very special. Here y appears only in one place. Yeah, so actually if you analyze it, it will come out to be D. 2D square is that easy bound. This will actually come out to be D, so let us note that. It's not very important, but good to know. So it's not 2D square, but much smaller. It's actually D, at most D. And then when you further take GCD, it cannot increase. So degree of H1 is also at most D. Right, so these are all low degree polynomials. So every step here you can actually efficiently compute. Right, in deterministic polynomial time, maybe even slightly cubic time, you can do all this. This is all happening in cubic time, subcubic time. In fact, all the steps. Are doable in polynomial in D log Q. Time. Okay, so Berlekamp had a factor of P also, so that is now gone. Okay, this is truly polynomial in the input size. Input size was D log Q. D many monomials in F, and each coefficient log Q bits. Right, so it was really D log Q, and you are doing everything polynomial in that. Any questions? So this is the reduction. So Berlekamp is an algorithm that is practical when P is small, characteristic is small. Even when it is not small, if it is very large, like 1000 bits or whatever, Berlekamp is actually an efficient reduction. It reduces field extension factorization to prime field factorization.
Sir, where is that thing getting handled? Like you said, polynomial may be irreducible in prime field, but not in F Q.
Yeah, then each one will be degree, each one will be 1. So nobody says that H1 is degree 1 or more. H1 may just be 1. No factorization happens.
In fact, because of this reason, degree of H and H1 will differ.
Yeah. Yeah, those things are dependent on F. So we are only giving upper bounds here. So this gives you the corollary. About FP root finding. So in this business of polynomial factorization over finite fields, you now have to solve only one problem, which is finding FP roots. Okay, you don't need to find quadratic irreducible factors, cubic irreducible factors, and so on. So you only need to find linear factors, which is equivalent to finding roots. And roots are remember they are only numbers from 0 to p minus 1, right. So, if you can just find FP roots, then you can solve everything because of this reduction. In this reduction, ultimately H1 only has roots and they are all distinct. So, that is that corollary we note that for polynomial factoring over FQ, it suffices to factor an F which is in FPX that completely splits into distinct roots. Okay, so completely splits, that is an highly non-trivial thing, and distinct roots. Okay, so from this point on we can forget about factor finding and we can only talk about FP roots finding, right, because any other problem can be solved using this with minimal overhead.
Sir, that's FQ in the first.
Called factoring over.
Yeah, that's true. Yes, and we always take P to be prime. Any questions? Right, so that is the state of the art of Berlekamp algorithm and all its connections. But this has still not solved our very basic problem of finding FP roots when P is very large. Right, that is actually, you will see in future applications that this is a very realistic practical problem, that you have a polynomial over a prime field and you want to find a root. For example, you may want to find square root of a number when it exists, right. You are given a number A modulo P and you want to take square root of A modulo P. So, either it will exist or not exist, which you will be able to check, but when it exists you want to find it, and that you still have not solved that problem, right. So now we will see an algorithm that solves those problems. So for exponentially large P, so a new idea is needed now. It's very old fashioned. Okay, and we will actually need randomization. Okay, so this essentially one fundamental algorithm, and it is called Cantor-Zassenhaus. It was given by Cantor and Zassenhaus. So we'll call it CZ. Yeah, so we have to develop few concepts in prime field before we can describe this. So let us prove some basic properties first of prime fields. So we'll assume that P is odd, P is an odd prime. Why can we assume that? What happens if P is not an odd prime? Then the only possibility is P is equal to 2, and what do you do then? 0, 1. No. P is the characteristic. FQ can be anything above F2. Yeah, so all those problems are already solved by Berlekamp, right? So P equal to 2, any Q which is a power of 2, that key, those factorizations you already know. Efficient algorithm, so those you don't have to solve. Yeah, okay, and yeah, when you look at H1, then H1 is only, it can only have 0 or 1 value, correct. Yeah, and then on top of that there is whole Berlekamp machinery to take care of factorization. So we'll take P to be large, so definitely odd, and F as before. So we have already pre-processed F, and we are at the point where F just has FP roots, distinct, and no other factors. So you look at two distinct roots of F, let's say alpha 1, alpha 2. Okay, and so we somehow want to separate them. So factorization is basically separating the roots, right? So that separation we will do by transforming F. And the way we will transform is the simplest way possible, which is by linear shift. So if alpha 1, alpha 2 are roots of F, what are the roots of G? Alpha 1 minus A and alpha 2 minus A, right? So alpha 1, alpha 2 have been perturbed by A, right? So when you perturb these two different elements, alpha 1, alpha 2, maybe their properties become different and you can distinguish such that their roots okay, let me be specific, such that the roots of G have different properties, and the specific property I am looking for is called quadratic residuosity. So what is the meaning of quadratic residuosity? Whether a number is a square or not, right? If it is a square, it is called a quadratic residue. Otherwise, it is called a quadratic non-residue. So alpha 1, alpha 2 are the roots of F. For G, they become alpha 1 minus A, alpha 2 minus A. And the question is whether one of them is a square, the other is not. Okay, so we want to make the residuosity different by choosing an A. Do you know ways to check residuosity? How do you check this?
Gauss
law.
Yes, Gauss's law is complicated. Something simpler than that we'll use. We'll use this thing, a to the p minus 1, or alpha to the p minus 1 by 2.
You can also take GCD with x raised to p minus x.
Yeah, but that is the same as alpha to the p minus 1 by 2. So we show that alpha is a square let me shorten this as QR. Okay, so alpha is a square or a QR. In FP if and only if alpha to the p minus 1 by 2 is 1 mod p. Okay, so we'll show that it is very easy to test whether a number is a square or equivalently a number is a quadratic residue. Okay, so all you have to do is raise it to p minus 1 by 2. P is odd, so p minus 1 by 2 is an integer. So you just multiply alpha that many times and get 1. So what is the other value you could have gotten? Yeah, why only plus minus 1?
Because alpha to the p minus 1 is 1.
Exactly. So note that by Fermat's little theorem, alpha to the p minus 1 was 1. And this is the square root of 1. And in a field, there are only 2 possible square roots. Both of them you know, plus minus 1, right? So this value could only be plus 1 or minus 1. So we are actually going with plus 1. And when you get minus 1, then all those alphas are quadratic non-residues or non-squares. So it's a very simple test. What is the proof? You can give multiple similar proofs. The easiest one is you use the cyclic nature of Fp star. So let G be a generator. G is also a polynomial. Let me not use G. So let gamma generate Fp star multiplicatively. And so then you can express alpha as gamma to the I, right? Actually, one side is quite simple, you don't need gamma. So the first side, if you want to show forward implication, so suppose alpha is a square, beta square, then what can you say about alpha to the p minus 1 by 2? So that is beta to the p minus 1, which is 1. Right, so the forward implication is clear. RHS has to be 1. Let us now look at the converse. We'll need gamma there. So say alpha to the p minus 1 by 2 is 1, which means that gamma to the I is 1, which means
I by 2 isn't here.
yeah, so what is the order of gamma? So p minus 1 has to divide it. Because I mean no number below p minus 1 essentially, yeah, since the multiplicative order of gamma is p minus 1, gamma raised to anything, if gamma raised to m is 1, then m has to be divisible by p minus 1 by the order. So let me write it that way. So okay, p minus 1 is the order of gamma, and that has to divide I p minus 1 by 2. Okay. This is in fact if and only if, which implies that I is even. Okay, this is also if and only if. So
Gamma to the I by 2 is a square.
yeah, which means that alpha is a square. So, this in fact is all you needed. Okay, this is a proof for both sides. So, kind of this discrete log of alpha, right, discrete log of alpha with respect to gamma is I. This I has to be even. I is even if and only if alpha raised to p minus 1 by 2 is 1, which is then equivalent to saying that alpha is a square. Any questions? So, in the literature in number theory, this plays a very important role, alpha to the p minus 1 by 2. Okay, this is a very important function of alpha. So, think of the finite, the prime field being fixed to fixed by p, and then this is just a function in alpha there from fp to fp. In fact, this is from fp to, what is the image? Yeah, this is from fp to 0 plus minus 1. It takes only 3 values, and it has these nice properties that it is multiplicative, right. So, this function for alpha, this function for beta, and then this function for alpha beta, those 3 things are related by multiplication. So, this is a very important, so this is a character of fp, and it is called, it is denoted also by this notation, alpha divided by alpha by p and bracket. Okay, it is denoted by this symbol, and it is called Legendre symbol. Okay, so this is the Legendre symbol. It is a character function of this group fp star, multiplicative.
This directly will be just plus minus 1.
Yeah. So, yeah, sometimes we may use this notation alpha by p as a shorthand. When p is not a prime number, let us say p is a general composite, then also this symbol is defined. It has a different name, so that we will use in the future. Okay, so for now, just this is just a basic thing we have introduced. Okay, so as you vary alpha, how many times is this symbol plus 1? P minus 1 by 2, right? So, around half. So, around half the time this is plus 1, around half it is minus 1, and it is a famous conjecture, or in a way also proved, that this is a random phenomena. Okay, so when you look at very, very large p, so as you are going from alpha equal to 1 to alpha equal to p minus 1, the way this plus 1 minus 1 distribution is coming, this distribution is nearly random, and this is proved by proving the Riemann hypothesis over finite field. Okay, so this randomness statement is actually Riemann hypothesis statement. There is a proof for that. But here we only need this probability estimate. So, probability over alpha such that alpha is a square. Let me make it a fp star. We will never take alpha 0. Probability that this is a square is what? P minus 1 by 2 divided by p minus 1. Yeah, okay, maybe let us go back to fp. p which is less than half. Okay, so but that is not correct. Then I have to take p minus 1 by 2 plus 1. So over Fp star it is half are squares and half are non-squares. Okay, this is, so we note this. Proof of this is simply you write alpha as gamma to the I, gamma is the generator before, as before. And note that alpha is square if and only if I is even, right, and I is even for half the time, 0 to p minus 1. Yeah, actually 0 to p minus 2. So this I actually runs kind of mod p minus 1. So here it is going from 0 to p minus 2. Correct. So this p minus 2 is odd. So in this interval you have half evens and half odds, right? That is the distribution.
So why you are taking p minus 2?
Yeah, because gamma's multiplicative order is p minus 1. So here the arithmetic happens mod p minus 1. This is important. This mod p in the base changes to mod p minus 1 in the exponent. Yeah, so with this with these properties now we can actually see Cantor-Zassenhaus easily. Cantor-Zassenhaus is directly based on these ideas. So the idea is that you pick a random element A. Okay, this notation means that you are picking A from 0 to p minus 1 by flipping coins. So how many coins will you have to flip to discover A? Right. So A has, or in fact, elements in Fp require log p bits. Right. Each bit will cost a single tossing of a coin. So A will require log p random bits, which is not too much. If you have a coin, you can flip it those many times. So then you would have picked A. So then it's expected that the roots of okay, I am making it f of x minus a now. Let me change before. So the roots of f of x minus a have different residuosity. Right. So say original roots were alpha 1, alpha 2. New roots are alpha 1 plus a and alpha 2 plus a. And say these two roots have opposite residuosity. Okay, one is a square, the other is a non-square. You know how to test for square, right? How do you test that? So you will take GCD with x to the p minus 1 by 2 minus 1. So, because of this property that you saw before, alpha to the p minus 1 by 2 minus 1, right, you know that any square has to be a root of this, and this has exactly p minus 1 by 2 roots. So, the roots of these actually are clustering all the squares. So, if you take the GCD of this with f of x minus a, then alpha 1 plus a will come out if and only if it is a square. So, if you can distinguish alpha 1 plus a from alpha 2 plus a by residuosity, right, then they will be separated. So, f will be factored. I mean, f of x minus a will be factored, but since you know a, f is also factored. Is that clear? Yeah, repeating will not help probably then. So, let me write, say alpha 1 plus a, alpha 2 plus a, or you can only look at one root actually, two are not important. So, say alpha plus a is a root, is a 0 of this f x minus a, and say it is a square. So, do you see that alpha plus a will be a root of the GCD also? Right. So, the square, the roots of the zeros of f of x minus a, which are squares, they will all be clustered out when you take GCD. So, if in f of x minus a there are two kinds of roots or zeros, then you factor it, right. So, your goal is to pick an a such that f of x minus a has different kinds of roots. So, at least one root should be there which is a square, and at least one root should be there which is a non-square. If all of them are square, I mean, this game you could have played already with fx. So, in fx, if if there is a root which is a square and there is a root which is a non-square, both of them are there, then when you take GCD with x to the p minus 1 by 2 minus 1, f would factorize. So, actually the bad case is when f has either only squares as roots or only non-squares as roots, in which case you will shift by a and try to make them different. If they are different, then GCD factors. So, that is the algorithm. So, Cantor-Zassenhaus algorithm is very simple to implement. So, you are given in the input a polynomial in fpx of degree d, and it is pre-processed. So, all the usual assumptions hold. In the output you want to give a factor. Okay. And it essentially has only one step. So, this one step is output the GCD of f of x minus a with x to the p minus 1 by 2 minus 1. Okay, this is a factor of f of x minus a. Let me slightly change this. So, I mean, if you can take GCD of f of x minus a with that polynomial, then you can as well take GCD of f with x plus a to the p minus 1 by 2. So, that is what we are taking, and whatever answer you get, you output it. Okay. So, if your choice of a was lucky, then in f of x minus a, there will be two roots which have opposite residuosity. Okay, and with that luck, GCD will factorize f. Okay, so there is only one step. So let us analyze this. So in the analysis, I'll prove both the things because it is not clear whether such an A even exists. Right? If it doesn't exist, then random choice will have no meaning. I mean, it will not help. Second issue is about efficiency. So suppose A exists, but only one or two A's exist. So then by random choices, you will never find them. It's impossible to find them. Right? So at this point, both the existence and the density is unclear. So we'll prove both these things actually in one step in the analysis. So let alpha 1 different from alpha 2 be the zeros of fx. Obviously everything in fp. So this is the notation I use for zeros. And so then this means that alpha 1 plus a different from alpha 2 plus a, both of them are zeros of x minus a. And suppose they have the same residuosity. So what is the equation for that? Alpha 1 plus a to the p minus 1 by 2 is the same. Right. So when you multiply it p minus 1 by 2 times, you get the same sign, plus minus 1. Think of this as an equation in A, unknown A. What is the degree of the equation? Minus 1, because the highest power of A will also cancel out. So view this as, so it is an equation in unknown A of degree p minus 3 by 2. Now for an equation of degree p minus 3 by 2, how many roots can be there? Which is very small. So this means that number of bad A's is less than equal to p minus 3 by 2. Right, which means that number of A's that discriminate alpha 1 from alpha 2, or let's be precise. So number of A's for which one fails is a lot. right. So, that is yeah, we can also consider a equal to 0. It will not change anything. So, number of bad A's above is limited by the degree. So, number of good A's, which means that they are able to discriminate alpha 1 plus A from alpha 2 plus A via residuosity, right, that is p plus 3 by 2, which is at least half. So, more than half of the A's are good, right. So, not only do they exist, their density is also 50%. Now, it does not matter actually where they lie in this interval 0 to p minus 1, it does not matter where they lie. If you randomly pick with more than 50% chance, it is a good A.
Sir, can you say again once why the degree is p minus 3 by 2?
Oh, why the degree is p minus 1 by, so what is the degree of A in the LHS? P minus 1 by 2,
Yes.
and the A raised to p minus 1 by 2 term both sides cancel, so it is 1 less. It is not an important point. I mean, it's even with p minus 1 by 2 degree, you get essentially the same thing. That density of good A's is half. So, what you deduce is that probability over A in FP, that the Hx that you are outputting, Hx is non-trivial given that F factors. I mean, that is already in the pre-processing, so obviously F factors. So, let me not even say that. This is more than half. Okay. So, probability that for a random A, your Cantor-Zassenhaus algorithm will factor F. This is at least half, and time complexity is clearly polynomial in log p. In fact, you can even calculate it other than the pre-processing step. This is just GCD, so it is again quadratic time or slightly more in log p, in D log p. So, this is a very fast, very practical algorithm. In fact, one of the only algorithms useful in practice to factor any polynomial over any finite field, right. Yeah, we can write the time also. So, this is for repeated squaring. I mean, again this GCD computation is possible only because of repeated squaring. This is a very special polynomial, x plus a to the p minus 1 by 2. It is exponential degree, but then it is a single exponential. So, you can compute it by repeated squaring mod f. So, you square, then you divide by f, then you again square, then again divide by f. So, that will go on for log p steps. So, there are log p multiplications and then division and then GCD. So, log p times linear in D log p plus the eventual GCD is O tilde D log p. So, which is O tilde D log square p. Okay, so, it is merely quadratic in log p. In D, it is actually linear time. Right. So, it is a very fast algorithm, although there were these pre-processing steps which were expensive. Pre-processing took around cubic. That is for the GCD. The D log p after the plus is for GCD. The first one is for reducing exponential degree second polynomial. this x plus a to the p minus 1 by 2. That is the dominant complexity. Okay. Yeah, so if you look at the overall factoring algorithm, overall factoring takes around there is this d raised to omega in the pre-processing it was actually d cube, but I mentioned that if you used fast matrix multiplication methods you can actually make it faster. So this will be something like d raised to 2.4 or 2.41, and there are obviously log q terms. I forget, maybe you will do in square. So this much time. Okay, it is subcubic. If you want to, so when you combine all these components of factorization, this irreducibility testing, then Berlekamp, and then Cantor-Zassenhaus overall. There are improvements to this. So Kedlaya and Oman's few years ago gave a sub-quadratic time method. So its time complexity is something like d to the 1.5 log q plus d log square q. Okay, so this is instead of d to the 2.41, this is d to the 1.5. Okay, it is sub-quadratic. It is still not linear time, but this is the best known. So polynomial factoring from the very beginning over finite fields, from scratch you can solve in this much time. Okay. Any questions?
Is it the same amount of random?
Probably. When you randomness is only from this picking of random points in FP. So that isn't too much. It is the other linear algebra steps, etc., which is costly. Okay.